Hello everyone. Thank you so much for joining me for another live Q&A today. I really can see you guys are asking your questions. I just want to welcome Fatima, Abby, Donna, and another Abby. So welcome guys. Thank you for joining me. And Fatima actually says this is perfect timing because I have a final tomorrow. Perfect timing. I'm glad. Then yeah, definitely ask me your questions, Fatima. I'll be here for an hour. So let's start off with our first question from Abby saying, determine the chlorine ion concentration. So we'll find our chlorine ion concentration after 100 milliliters of, let's see all of our different concentrations that they give us. After I write all this down, we'll build a balanced equation and see what we're asked to find. So 100 mils of something else, another molarity or concentration. Okay, and then assume, or also determine the mass of our solid formed. Okay, so we're looking for multiple things. We're looking for the concentration of chlorine ions and the mass of our solid or precipitate. Okay. Why don't we just start off with a balanced equation, and then we'll use our solubility table to see which one is going to form the solid or precipitate. So we would combine magnesium chloride, and we'll add that to silver nitrate. And once again, that whole trick of predicting products where the inner and the inner elements go together, we want to put the metal first, then the non-metal. So silver would be first, that has a +1 charge, and then chlorine has a -1 charge. Those are totally fine in our charges. So then this would have just been silver chloride. And then the next part, we'll combine magnesium and nitrate. And then remember, magnesium is going to be first since that's the metal, but that has a 2+ charge and nitrate has a 1-. So I have to put a 2 subscript, and I'll put that on the other side, and then we'll balance everything out. So this would have been magnesium, and then in parentheses, nitrate with a 2 subscript. Okay, so now that that's set, let's go ahead and balance everything out. So I'm going to separately bring back that G, there we go. So I'm going to separately put all of our elements on either side, and then we'll start balancing everything out and make sure what we need. Okay. And then after this, we'll see, because this tells us the ion concentration, I want to look at the net ionic equation as well, okay? And it's just because they're telling us it's ions. So that tells me, oh, I most likely will have to build this, then do the whole complete or total ionic by breaking every single aqueous compound into its ions. And I'll do that with you. But let's see, magnesium would have only been 1. There's 2 chlorines, 1 silver, and 1 nitrate. Opposite side, there's 1 magnesium, 1, 1, and 2. Okay. So I'm just going to start off with the chlorines, and I'll put a 2 on this side. It's like you're distributing, and now we have 2 chlorines and 2 silvers. And then now everything else stay the same. So I need to balance out the silvers and the nitrate by putting a 2 on the opposite side. That would distribute, and you'll note that now we are balanced. So perfect. Next thing, let's predict what their states are. So whether it's aqueous or a solid, and so on. So if we were to look at our solubility table, and how I look at that is I look at the ending, like the nonmetal. So I look at the end and I see, well, chlorine is typically soluble, so this is actually going to be aqueous. All nitrates, NO3s, are always aqueous or soluble. And then same thing with this opposite side where this has to be aqueous no matter what because nitrates are always soluble. However, for sulfur, that's going to be our solid. Okay, so that one's going to be our solid, and what I'm going to do is I'm going to break everything down, do the whole total or complete ionic equation, then cancel out what I can and go from there to the net ionic equation. So let's start off with magnesium chloride, breaking this apart into its separate ions. So starting with just magnesium, putting the charge, and putting the state that it's aqueous. Now here there are 2 chlorines. Once again, I'm going to put that's aqueous. And then I'm going to keep going. And then here there are 2 nitrates and there's 2 silvers. So I'll put that there's 2 silvers with a plus charge, and that's aqueous. And then next I'm going to put plus another 2 NO3 minus aqueous. Okay. And then we'll keep going. Now, we never break apart the solid, so we'll leave that intact. So that's not going to change whatsoever. But this will break apart since it is aqueous. So we'll have magnesium with a 2+, and that's aqueous, plus 2 nitrates, and that's also aqueous. Then we'll cancel everything out of this total ionic equation. Okay. So now let's cancel our spectator ions, so anything that basically is the same on either side. So I'll cancel out the magnesiums. Well, we could also cancel out the nitrates, and that's about it. So what will remain is whatever ions remain are those that combine to form your solid. So in this case, we would be left with 2 chlorine ions plus 2 silvers. And this is going to help us because we want to figure out the concentration of chlorines. And essentially, since there are 2 or double of that, I will have to double this in a second. And I'll show you what I mean. So this is what we would get. Okay. So that's what we would get. And then actually even looking at this, since they all have 2s, what we can do is actually remove the 2. And that's totally fine. It's kind of like you're simplifying in a way, just because if they all have a common factor, you're allowed to simplify it. So that's actually the balanced equation or the net ionic equation. Now I'm going to go back to all the information that they gave us before. So since we're looking for concentration, that means we want molarity, which is moles divided by the total liters. So I'm going to start off with the concentration that they gave me before, which was, actually they gave us 100 milliliters of magnesium chloride. And then this formed, actually this was of 0.0100 molarity. Okay, so what I'm going to do now is I'm going to figure out the amount of moles of magnesium chloride and then work my way to get to the moles of just chlorine. So, and I'll show you how to do that. So if I were to have 100 milliliters of magnesium chloride, I'm going to change this to liters so I can cancel that out and then get to moles. So then this would have been 1,000 milliliters on the bottom, 1 liter on top. All right, and then I'm going to keep multiplying. And I'll multiply this by the molarity or concentration that they gave us, where 1 liter is on the bottom and our moles are on top. Okay, and this is still of magnesium chloride. So that's the amount of moles of magnesium chloride. And then let's multiply that out, see what that would give us, and go from there. So we multiply everything out. Okay, that would give us 0.001, and that's moles of magnesium chloride. Okay, and then let's see what else we can do with this question. So they are asking for the concentration. So, okay, I will add those volumes in a second, but let me see what else I can do. So because we're asked to find here, let me see what else I can do with this. Everything's 1-to-1, because typically they give you grams, but that's okay. We can figure that out. We could actually figure out the grams by using the molar mass of magnesium chloride and then going from there, which, you know what, I actually think I'm going to do. I can do that. Yes, I can. Yeah, let's do that. So I'm going to keep going with the moles, and I'm going to actually bring the molar mass of magnesium chloride. And let's just find the molar mass of magnesium chloride. Okay, so magnesium is 24.31 grams per mole. And then this would have been 2 times, there's a 2 here, so 2 times 35.45, which is 70.90. And then I'll add those 2 together, and this is going to give me the amount of grams, and then I'll go from there. Yeah. So plus 24.31, 95.21, and then so I'll multiply those 2 together, and that'll give me the grams of magnesium chloride. This is 1 mole. Okay. All right, and that would have been 0.09521 grams of magnesium chloride. Okay, so then since they were asking for, let's see, they were asking for the mass of the solid, which I'll get to as well. That one's not bad. I'm going to deal with the ions right now because that's like the trickier one. But now that we found the overall grams of what we started with, that's going to help us be able to get to just the, get to the grams of our chlorine. So let's see, after I do that, I can divide this by that. Yeah, that gives me the grams. I can divide this by the molar mass of the entire thing. Sorry, I know this question is a little bit tricky because they typically give you, that's fine. I actually don't even feel like I needed to convert it to grams, come to think of it. I just needed the moles and multiply that by, yes, sorry about that. I actually just needed the moles because, yeah. Okay. So I just needed the moles, and the reason why I just needed the moles was because I did that net ionic equation because I wanted to see how many chlorine ions there would have been at the end, which was only one, right? Everything was 1 to 1. So in that case, the amount of moles that we just found are actually the amount of moles of chlorine. So what I'm going to do now, because this is representing like the overall reaction, what I'm going to do now is divide it by the total volume. So those are here. If there was like, let's say a 2 in front of that chlorine, like Cl minus, when we were looking at the net ionic equation, then you would have multiplied this value by 2. So that's why I was checking. But in this case, we don't need that. So I'm going to actually state that these are the moles of our chlorine ion. And then from here, let's add up our total volume that they gave us. So 100 mils plus another 100 mils, so 200 milliliters. And then I'll convert this to liters because it is concentration. And then, so this would have been really 1, 2, 3, so 0.200 liters. We'll divide both of these, and that would give us the concentration, and then I'll show you how to get to the grams. Okay. 0.001 divided by 0.2. This would have been 0.005, and that would have been a molarity of Cl minus. All right, that's our concentration for that. Now, for the first part, where it's asking us to determine the mass of the solid formed, I'm going to take it from the amount of moles that we found before. And then I'm going to go back to pretty much what we found before with magnesium chloride. And then using and you know what, let me bring that up here so you can see what I'm going to use for our balanced equation. Here. So let's take it back to the balanced equation because it'll make so much more sense here. Where looking at the moles that we found before, the 0.001 moles of magnesium chloride. Now here I'm just going to do a multiple ratio to change the compound to the solid that we formed, or silver chloride. Then from there we'll use the molar mass and just convert it to grams. So this is going to be moles of magnesium chloride on the bottom, and there's only 1, right? And then there's 2 moles of our silver chloride. Okay, then I'm going to multiply this by the molar mass, which I have to figure out. This is 1 mole of silver chloride, and then that would be it. But let's figure out what our molar mass would have been of silver chloride. I know chlorine is 35.45, and then silver is 10, let's see, this amount. Okay, let's add those two together and see what we get. All right, this gives us 143.32, and then we'll multiply everything out, and that'll give us the overall mass of the solid. So let's see, multiplying everything on top, since everything's really divided by 1, our final answer would have been 0.28664 grams, rounding. Let's look at our sig fig count. So the amount of sig figs that they gave us were 3. So I'm going to round this to 3 sig figs. So this would have been rounded up to 7. So 0.287 grams of silver chloride. All right, that would be our final answers. Okay, that would be it for that one. Let me make some room to answer the next question. All right, our next question, and then real quick, Abby asked, I'm not sure whether it's a dilution problem or not. So with dilution problems, what you would see is like the instant thing that I knew it wasn't going to be a dilution question was because they gave me two different molarities of two different compounds. So if it's a dilution question, it has to be the same solution. Like if it were magnesium chloride, or even, let's say, yeah, even that. So magnesium chloride, our first molarity would have to state it's magnesium chloride. The second molarity would still have to be magnesium chloride. It wouldn't be able to change. So that's how I know it's a dilution problem. If it wouldn't be a dilution problem like this case because there was two different solutions. Okay. And let's see the next one. So another Abby states the total pressure exerted by a mixture of 1.5 grams of H2 and we have 5 grams of N2. We're also given the volume is 5 liters and our temperature is room temperature 298 Kelvin and we're looking for our pressure. Okay, so this is going to have two different steps mainly. The first thing is we have to figure out how many total moles we have in the mixture because we want to get to using PV equals nRT or our ideal gas law. So since I want to solve for P, I don't have enough information. I need to figure out what N is first. So let's just start off with converting those grams to moles. So 1.5 grams of H2 as well as 5 grams of N2. After we do that, we'll add them together. That'll give us the total moles of the mixture. So I'll divide everything. Our molar mass for H2 would have been 2.02 and 1 mole on top. That's of H2. Okay, and then I'll do the same thing for the other. I'm just going to set it up. So for N2 would have been 14.01 times 2, which is 28.02. And I'll put that on the bottom and convert to moles. So let's see what we get with that. So 1.5 divided by 2.02. This is 0.74. And I'll leave it as that. That's fine. So moles of H2. Next, 5 divided by 28.02. That would give us 0.18 moles of N2. Now we'll add those two together, and that'll give us the total amount of moles. So N total, after adding both of these, let's see, this gives us 0.92 moles. Now we can plug it into the ideal gas law. So I'm just going to rewrite this formula, and I'll solve for P just to make it easier. So I'll divide V to both sides. Those cancel. And then our actual formula is really just P is equal to nRT divided by V. Plug everything in, and that'll give us the pressure. So N we stated was 0.92 moles. R is 0.0821 liters atmospheres divided by moles Kelvin. And then our temperature was that 298 here. So 298, and then we had 5 liters. Yeah. Okay, so your moles will cancel, liters will cancel, Kelvin will cancel, and we'll be left with atmospheres, which is what we want. So let's multiply everything together and see what we get. Divided by 5. So our pressure would have been 4.5 atmospheres. And that would be it for this question. Okay, hope that makes more sense. And let's look at our next questions. Donna. Hello, Donna. Welcome back. Can you do a brief explanation of the difference between Lennon dispersion forces and dipole-dipole moments? And you give an example. Perfect. So what types of intermolecular forces are expected between? Sure. C2. Okay. Okay. So let's, even before doing this, just looking at Lennon dispersion, I'm going to call that LD, and then dipole-dipole here, just to understand what everything is referring to. So dipole-dipole are, it's pretty much any sort of structure that's polar. Okay, that's what we look at for a dipole. So any sort of molecule that's polar. Now, London dispersion is actually nonpolar. Those are the main differences between them. Like you could have something like that is polar, where that could have been, let's say, let me just think of one. Sure, something like this. Something like that. Okay. That would have been polar because our chlorines are very electronegative compared to hydrogens. And think of it as that pool of electrons. This is what polarity is talking about. It's stating that one of the, like there's an unequal pool of electrons is what I want you to think of. So chlorine has that kind of advantage that it's more electronegative compared to hydrogens. And so it would pool those electrons in that direction, causing something known as a dipole moment. So in other words, I kind of think of it as a tug of war between elements, where if one wins, then that means it's polar. If nobody wins, that means it's nonpolar. So here, this would have been polar. Now, if it were to be, let's say, something like this, where there's just hydrogens all throughout, and it's completely symmetrical, or I could even state the same thing if it was just a bunch of chlorine surrounding it. As long as it's symmetrical, that means there's equal forces. So think of it as like, the same person is battling against their own strength. Well, nobody's going to win because it's equal strength or equal forces. So that's why it would have been nonpolar, since it all cancels out. So that's the main difference between London dispersion and dipole-dipole. Now, if we were to look back at this question, let's just see, is there going to be polarity? That's kind of like the main difference between this. So let's kind of look at how many valence electrons there are and then draw this out. So for carbon, that would have been 4. And then Se, that would have been 6. Multiply that by 2. I'm adding everything up, so 4 plus 12, and that gives us 16. Our carbon is going to be our central atom because it always is. And then this is going to be surrounded by 2 different atoms. And then I'm just going to put all of the electrons on the outer elements, and then if I need any more, I'll put them in the center. So putting everything together, a trick of mine, just to kind of make this simpler, instead of having to count every single electron, is whenever there's only one bond and there's 3 lone pairs, that's going to make 8 electrons. So this would have been 8 electrons, so I just have to kind of multiply. 8 times 2 would have been 16, so far that's the correct amount of valence electrons. However, our central atom is not happy because it wants to have a full octet. So in this case, I would move and form that double bond because carbon favors higher bonds rather than any like lone pairs on the carbon itself. So this is what it would look like. So instead, we would basically remove these, and they're now double bonds. Okay. So looking at this, it's symmetrical, right? There's no unequal pool of electrons. Everything's completely equal since we have the exact same atoms on either side. So in this case, this would have been nonpolar. The fact that it's nonpolar and there's no hydrogen bondings, right? There's not even hydrogen at all. Then that means this is just going to be London dispersion. That's the main difference and main factor. And let me see if I can put a video in the chat. This is intermolecular forces. I do have a video that helps you, go over what every single type is, as well as there's a practice problem at the end that shows you how to like list it in increasing order, I believe. And then I have a bunch of examples as well. So make sure to check that out. It's really helpful. So I'll put that video in the chat. It's called Intermolecular Forces. Okay, let's see what else we have. Okay. I have someone saying, tomorrow I have a test about calorimetry. Can you explain it to me, please? What about calorimetry? So let me know. Yeah, let me know, just because that is a bit of a broad concept. Calorimetry, whether it be, Q equals MCAT, I can quickly go over what Q equals MCAT. That's the main thing for calorimetry, but there's a lot of aspects to it. But I'll quickly do one and explain how you would use this. But let me know if there's, if there's something specific just to help answer your question better. But here, let's just say, let me pick a calorimetry question. So for everyone joining, if you guys have specific questions, that helps me out a lot, just because I know I'm I can be talking about, like, let's say thermochemistry or so many different things, and there's so much to it. So to better answer your question, if you have a specific question, that helps me know what you're struggling with and what to, you know, help you out with. So just a little heads up. So let me grab a question for calorimetry. Okay. Let's say, and then even before doing so, let me just explain what every single little part of this formula means for everyone who's struggling with calorimetry. So Q is heat, and that's going to be measured in either joules or kilojoules. And then M represents our mass. That's going to be in grams. And then our CS, or even C, that's going to be our specific heat capacity. So specific heat capacity. And then these units are going to be joules divided by grams per Celsius. And then our delta T, or that little triangle, just means change. So this is our change in temperature, which really it's our final temperature minus our initial temperature. Okay, so understanding this formula is going to be very helpful. By the way, our temperature is measured in Celsius. Okay, so let's just start off with an example for some sort of calorimetry question. Let's say we were given that, let me go back. There we go. So let's say the specific heat capacity of iron was 0.450 joules per grams Celsius. How much heat? So I'm going to say C is equal to this, and then how much heat is released to, and actually, let me say absorbed, to raise the temperature of a 5-gram sample from 22.0 degrees Celsius to 53.0 degrees Celsius. Okay, so what I'm going to do is just identify what we have and then what we're solving for. One little note, by the way, whenever it's saying heat is being absorbed or released, that's really important to note. Whenever heat is being absorbed, that means that our heat, or our Q, will be positive. Whenever our heat is being released, that means it will be negative. Okay, so make sure to pay attention to that language, because they're not going to, they're really not going to tell you that, oh, it has to be negative, it has to be positive. They're trying to get you to understand that concept, and technically they try to, you know, get you with that little part. Okay, so beware of that. So let's figure out what we have, and let's plug everything in. What I'm going to do is start off with our change in temperature. So our T final is going to be the second one. Okay, and then our T initial will be the first one. So this is 22.0 degrees Celsius. This is 53.0 degrees Celsius. Our mass was 5 grams. And then we really were given our specific heat capacity. So all I have to do is plug it into the formula. So a lot of people think of this as, or how they remember it, as Q equals MCAT, because it looks like MCAT. So I'll plug in everything where this is 5 grams, our specific heat capacity, joules per grams Celsius, and then I'll subtract those two temperatures. So final minus our initial temperature. Okay, so, and this is all in Celsius. So let's do all of this math. If I were to subtract these two, this would have given us 31 degrees Celsius, and then we'll multiply all these values. And you'll note that your grams and grams will cancel, your Celsius and Celsius would cancel, and you're left with joules, which is what heat is measured in. Okay, so I've also seen it in kilojoules, just depends on what they're asking. So 5 times 0.45 and then times 31. This would have been 69.75 joules. And then we can, I would say we'd round up to, let's see, however many sig figs they gave us initially, which I believe was 3. It was 3. So I would stop here. So 69.8 joules. And since it's absorbed, it's going to be positive, which it already is, and that's fine. Okay, so that's a basic calorimetry question. Let me know. I'm going to keep answering other people, but definitely let me know if there's more questions, and I'll get to it as well. Okay. Let's see. the next person. So Jessica says, hi, Melissa. Could you please explain the Born Harbor cycle? Yeah. Okay. Let me grab an example because these are a little bit longer. Here. Let me grab an example because, like I said, these tend to be a little bit trickier. Okay. Sure. Let's see if we were to have... Okay, I just needed all my values. So let me see if I can pick another one that isn't this crazy. One sec. Let me see if I can find another one that I have. I think I really have one. There we go. I just need all the like constants and values that they give us. Okay, I think I have one here. I do. Let's see. Okay. So let's say if we were asked to find, or actually, sorry, I'm debating on which one I want to do. Let's say if we were asked to find our lattice energy. Okay, so even before doing this, let me just give you what the formula would be and would entail. Here we go. Okay, so let me give you the formula. This is going to be really helpful to pretty much do all of these questions. So let's say if I were to find the overall enthalpy of formation, that's what this means. F means, okay, so that's going to be a formation of some sort of solid. And then this is going to equal our enthalpy of sublimation. Okay, sublimation meaning we're just going from a solid to a gas. And then I'm going to add this to our enthalpy change for bond energy. Remember, bond energy is when we're like either breaking or forming bonds. And then next, our change in enthalpy for ionization energy. I'm going to say IE. Okay. Why isn't this writing? There we go. Plus our change in enthalpy of electron affinity. And then lastly, our change in enthalpy of, I'm going to label this LE, lattice energy. By the way, what lattice energy is and what it does, what lattice energy is, it's the energy required to take different gases and basically combine them and compress them into some sort of like solid crystal. Okay, so that's kind of like the easier way to think of it. Like just think of it, lattice energy, the energy required to take two gases or gases in general and put them together to form some sort of it's called the lattice crystal, but think of it like a solid, okay, that we're compacting everything together. So now what I want to look at, let's say if we were asked to find, let's say magnesium chloride. Okay, so let's say if we were asked to find magnesium chloride, and that's our solid. So what I would start off doing is you're always going to start off with sublimation. So sublimation, it means we're taking the metal and we're taking it in its natural state, which is a solid, and we're actually going to change that to a gas. So the first thing would have been sublimation. I'm just going to put sub, meaning sublimation, where the equation for this would have been magnesium, and it's always the metal. It's in its solid state, and we're just going to show that it now changed to a gas. Okay, so for these to basically combine, they have to be in their gas form. And then this is basically what we would do with this is we would be given different constants or values. So sublimation would have been given as 147.1 kilojoules per mole. Okay, that will come into play later when we plug everything in. And let's say, by the way, we're finding our overall formation, enthalpy of formation, okay, of this solid. So then next, what I'm going to do now is I'm going to go to bond energy. And bond energy, remember, was the whole breaking bonds and forming new bonds. So in this case, I would have found that chlorine, is diatomic and it exists already as a gas. However, I only need one. So since I only need one, I'm actually going to chop this in half and say this is going to be chlorine and so on. Okay, so I chopped that in half. And before I do anything to the enthalpy, I'm just going to leave that for now, and I'll explain what to do later. But this is something that we would have seen. Okay, so that's 1/2 now. Now it's totally fine and that's balanced. And they would have given me the bond energy was 1 to 2 kilojoules per mole. Okay, and then the next part would have been ionization energy. So our ionization energy is the energy required to remove an electron. So in this case, our ionization energy is only going to be for the metal. Okay, ionization energy goes with the positive charge of the metal, while electron affinity goes with the nonmetal or the negative charged one. Okay, so in this case, for our ionization energy, sometimes you can have multiple ones. So if magnesium, if we were to look on the periodic table, we'd see that its charge is a 2+ charge. So since it's a 2+ charge, that means there will be 2 different ionization energies. If there was only a 1+ charge, then that would have only had 1 ionization energy. So in this case, I have to basically do every single ionization energy step by step. Okay, I'll start off with where it left off. Where it left off was a gas. Okay, where it was a gas, and that's now going to go to its first ionization energy, meaning its first ion or cation, and then I'll add 1 electron on the product side to make sure that everything's balanced out with our electrons. And then next, this would have just been our enthalpy of our ionization, our first ionization energy, which all of these values, by the way, will be given to you. They have to be. So this would have been 738 kilojoules per mole. And then I would do this again. Okay, so magnesium has a 2+ charge, so I'm going to pretty much do this again where I left off. So now this is a plus, still in its gas form. Now I'm trying to get this to be a 2+, and that's how it exists. And then now I'm going to add 1 more electron just to make sure these are all balanced. And this is the ionization energy, the second ionization energy. Okay, so this is here. Let me make this better. All right, change in enthalpy of ionization energy 2. This would have been 145 kilojoules per mole. Okay, we're going to keep going. And then now with this one, I have to do the electron affinity. So electron affinity is going to take place with our chlorine. So the chlorine that we left off with was Cl in its gas form. Now I have to make this into a negative charge. So since there's only going to be 1, because this only has a -1 charge, and then I'm going to balance this out again and put 1 electron. Okay, and then actually on the opposite side, because remember, electrons are negatively charged. So this is just to balance out our electrons. And then, perfect, that's it. And then this would have been our electron affinity, which will also be given. Okay, and this is -349 kilojoules per mole. All right, last step is after you've gotten everything in the correct state, and by the way, as I mentioned, lattice energy is taking gases, and one more little note to add with that, gases in their ion form, okay? So that's what we're trying to get to with this whole cycle and whole concept, is we're trying to get these, like this metal out of its solid state to get to a gas, and specifically to have it be an ion in its gas state. And then putting those together would form that solid or that crystal. So in this case, I would now combine our magnesium that we left off with, which was the 2+, and that's a gas form. I'd add that with the last part that we got where this was an ion and it is in its gas form. That would then combine to be magnesium chloride, and that's a solid form. I'm going to put a 2 there just to balance this out. And then this would have also been given, or sometimes they ask you to find the lattice energy and they would give you the actual enthalpy of formation. And then you would subtract using that formula. So this is lattice energy. This is -2522 kilojoules per mole. Okay, so next step is to make sure that everything adds up accordingly. So one thing to note was the fact that to balance this out, we needed 2. Okay, we needed 2 of them. Well, did our previous equation have that? No. So the fact that this didn't have, and by what I mean there, okay, was there was 2 chlorines here. However, that's not what I found here. And those need to add up and be the exact same. So I would actually multiply this entirely by 2. And when I'm doing that, I have to do the same exact thing with my enthalpy of electron affinity. And then now I'm going to go back and make sure, well, I didn't do that with this previous case. Right? I didn't put that there was 2 here either. And the reason why I have to do this is because if I were to add everything up, everything has to cancel, okay? So then this would be times 2 as well, and then I would have to figure out those new values. So here, the main thing to kind of take away from this was I would need 2 Cl gases. That's why when I went back to change this, that's why I had to put a 2 here, because now there would have been 2 Cl gases, and those, like I said, have to cancel. So next, the last thing is to add everything together, okay? So I would literally add this one, that sublimation. Next, I would multiply 2 times 122, and that would have been 244 kilojoules per mole. Okay, I would keep going, and then this is, I would add it to this value for our ionization energy 1. Same goes for, as you can tell, this is a very long question, but these tend to be. Then this would, I also would have added it to the ionization energy of the second half. Next, I would multiply 2 times that negative 349, and that would have given us a negative 698 kilojoules per mole. And then lastly, I would add it to the lattice energy that they gave us before. After I add up all of those values, so this is kind of similar to, it's a tiny bit similar to Hess's law, where you, whatever you do to your equation, you also have to do to your enthalpy change. So that's kind of something else to take a note of, but that's what it's kind of referencing. And then our overall formation after we add all this together would have given us this value, and we're finally done. Okay, so I think to me the hardest part would be remembering all of this, right? Remembering the formula, but this is how it's always going to look. And then this formula pretty much helps you kind of put everything step by step and put it, you know, all in order. So yeah, I hope that makes some more sense. I know these can be a little bit tricky, but luckily you'll be able to see the replay of this, or you'll be able to watch this once I'm not even on live anymore. Okay, so definitely review that, because I know these tend to be long. Let me move on to the next question. Okay. So positive is saying the concentration of each solution has been calculated using the dilution equation. What will the molarity of our solution, 12 milliliters of that molarity diluted to a volume of that. Okay, so we're looking for our second one. Okay. All right. So this is M1. Yeah. Okay, so why isn't this writing? Sorry. M2V2. So for this equation, I'm just going to plug in everything that we know. So they're saying what molarity of a solution, if 12.00 milliliters of, let's say that this is our V1, okay, that's our first volume, and then M2, or actually M1, would have been that first molarity that was given, and then we're asked to find our second molarity, and then next we're given our second volume. Okay, so all I have to do is pretty much plug in. Since everything is consistent, meaning I don't have to convert anything here, they're both milliliters, that's totally fine. However, if one of them were liters and the other one was milliliters, I would have to convert to, doesn't matter which one. It basically just means like we have to have them be the same thing. That's really it. Okay, so since they're both the same, they're both milliliters, I can just plug in. So I'll plug in everything. So M1 is going to be 0.40. That's molarity. This would have been times 12 milliliters. we're looking for M2, and then I'd multiply that by 50 milliliters that we were given initially. All right, so what I'm going to do first is I'm actually just going to divide over, and then we'll do the math accordingly. So all I have to do to get M2 by itself is get rid of that 50 by dividing it to both sides. So that would cancel. And then for people who are joining, this is a positives question talking about concentration and dilution. Yeah, so I'm doing dilution questions right now. So that would cancel out. And let's see what this would give us. What I'm going to do first is, by the way, these milliliters would cancel and we would be left with molarity, which is perfect because that is what we're solving for. Okay, so this would have been 0.40 times 12. And then I'll divide by 50. So 0.40 times 12 and divide that by 50. That would give us 0.096, and that would be our molarity. So it was really just knowing how to plug everything into the formula. A little trick for you. A lot of times I see students kind of look at like, oh, which one is M1, which one's M2. I don't know what's what. Whenever they give you, like, let's say, actually, a volume, like milliliters of some sort of molarity, okay? These two have to go hand in hand. Because that of, this goes back to math, of actually means multiply in math. So these two have to be the same thing, meaning like this has to be volume 1 and this has to be the molarity 1, okay? So that's going to be your hint. Whenever you see those two together, don't separate them. It's not like you're not going to have one that's 1 and the other one that's 2. That's never going to happen. All right, so that's something to kind of note. So now let's look at our next question. Let's see. Canwell saying, can you explain stoichiometry? I'm so confused. What are you confused on? So I am doing a little bit more specific questions. What I can do, like, let me know if there's something specifically, like, actually give me a question. I do have a whole playlist designed for stoichiometry, so I can put that in the chat, and that's going to help you a lot. So what I recommend with stoichiometry is knowing how to use your overall conversion factors, and that's using molar mass, Avogadro's number, and multiple ratios. So that's what you're going to see first in the playlist, and that's going to, I would say that's actually the absolute best way to go about it first. And then at the next video, it's going to show you how to put everything together into a problem. So for someone who, doesn't understand stoichiometry, it goes back to understanding the conversion factors. So I'll put that link in the chat right now, that playlist. And then I also have really, really detailed notes. It's basically like a guide to how to do stoichiometry in general. And what I included in there was, think of it as every single type of like problem that you can think of, like going from grams to moles, going to grams to grams, grams to liters, and so on. I put it in that huge note packet. So I made sure to put several questions that I've seen on exams and just what a professor or teacher would ask. So I'll also put the link to the notes in the chat as well. And for everyone who doesn't know, I do design my own notes for you guys. It's pretty much everything that I wish I had when I was taking chemistry. Think of it like a simplified version of your textbook, and it's not going to be as long. It's pretty much what you need to know. Okay, so I'll put that in the chat right now as well. Okay, so let's look at the next question. Let's see. And then for everyone also coming in, if you don't know who I am, I'm Melissa Maribel, not Marissa. Okay, so I know it happens. I get it. It's a common name. I've also been called Michelle. I don't know why. But yeah, it's Melissa. I just want to introduce myself. Okay, guys. So, okay. And then DG is saying, could you explain how you work out the problem? 50 grams of H2O was heated from 20 degrees Celsius to 50 degrees Celsius. How many calories? Okay, so Q could also be measured in calories. Were needed to bring about the temperature change. And this is of water. Okay, so what I'm going to do first, one, there's one little piece of information that's missing, and professors typically expect you to know this. So for water, the specific heat capacity is 4.184 joules per grams Celsius. And I know we want to get to calories, so we will convert joules to calories at the end. So this is like a two-part question, where let's just start off with plugging everything into Q equals MCAT. Okay, and then this is for everybody. What I'm doing, this is a little glimpse of calorimetry. So anyone who's struggling or has their exam on calorimetry, this is a good little overview. So I'll use this formula again. And what I'm going to do, let's just plug everything in where we're looking for Q. Our mass was the 50 grams of water. Our specific heat capacity is one that we had to know. This is, like I said, this is for water. Okay, this is for H2O. So definitely know that one. And then this is joules per grams Celsius. And our change in temperature is going to be final minus our initial. So our final temperature was the 50 minus our initial temperature, which was the 20. This is degrees Celsius. So let's multiply everything out. If I subtract these two, that gives us 30 degrees Celsius. And we'll multiply. So 50 times 4.184 times 30. This gives us 66276 joules. And I'm going to convert this now to calories. So let me grab all my little conversion factors because this is going to help us out. So it is known that 1 calorie is equal to 4.184 joules, and that's what I'm going to use to convert this to calories. So what I'll do is I'll just divide my joules, and then this would have been 1 calorie on top. Okay, so I'll divide those two values, and that would have been our answer. So Q is going to be this amount of calories, and that would be it for this question. Okay, and let me just make sure one little thing that it didn't say anything about absorbing or no, it didn't. Okay, so it is positive. Yeah, just I always like to check. Does it say that, oh, the temperature or actually the heat is being released? If heat is being released, this would have been negative. If it's being absorbed, then it would have been positive. And then since the temperature is actually increasing, that also helps you figure out that since it's raising in temperature, it's going to be positive. Okay, so that's this question. Let's see the next one. Okay. Let's see. So, Verna Daniel saying the pressure in an automobile tire. We have pressure. Okay, so let me just start writing everything that we have. So we have pressure. We also have our temperature. And at the end of the trip on a hot sunny day, the pressure has risen. Okay, so we have our P1. We have another pressure, which is P2. So that's going to be 2.2 atmospheres. What is the temperature of the air in the tire? Assume that our volume has not changed. All right, so whenever they're telling you, this is 1, this is actually 2. Whenever they're telling you that something is held constant, like let's say, you know, the volume's unchanged or the pressure's constant, temperature's constant, that just means it's irrelevant. Like we're not going to use a formula that has that. Okay, so instead, what helps me with these types of gas law formulas is to just write down everything that we're given, and then you'll note it's pretty much going to pick what formula for you. Okay, so in this case, we have to pick a formula that has only pressure and temperature, and this is the formula that you would find. It would have been P1 divided by T1 is equal to P2 divided by T2. Okay, and then we would basically plug everything in. However, make sure that temperature is in Kelvin. So for all gas laws, make sure that your temperature is in Kelvin. So I'm going to do that first. Let's convert this to Kelvin by adding 273, and that will convert it to Kelvin. So it's, let's see what this gives us. 300. Okay. Now that is done, I'm just going to plug everything in and solve for T2. All right, so plugging everything in, pressure 1 was 2 atmospheres. Our first temperature, we changed it to Kelvin. This was our second pressure, and we're looking for T2. What we can do is actually cross multiply. to make this a little bit easier on ourselves. So cross multiplying these two, that would have really been, and I'm going to pretty much remove the units, just to know that it will be Kelvin since we are looking for temperature. So this would have been 2T2, and then I'll multiply these two together, so 300 times 2.2, so 660, and then lastly all we have to do is divide that by 2, and that's our final temperature, which is 330 Kelvin. Okay, so that's pretty much my main thing for you guys with gas laws is to, one, make sure temperature is always in Kelvin, and after you've written out everything that you're given, the formula is kind of like hidden within there, and it's just knowing your formulas and knowing that, actually, real quick little tip, like this one is Boyle's law, right? This one that we just did, and so on, where this is volume and temperature. So the only ones that are going to be multiplied by each other and there's no division is Boyle's law and the ideal gas law. Okay, so everything thereafter is going to be divided. Now, does it matter if we were to flip these? No. As long as they're both flipped, mathematically speaking, it would still give you the same answer. So if you know that, okay, Boyle's law is the only one that's being multiplied, same with the ideal gas law, that's pretty specific, then everything thereafter would work if you're just dividing it. Okay, so that's something to note, little trick for you. Let's see if maybe I could answer one more real quick. At least see what you guys are struggling with, and then maybe I can put a question up. Let's see. So, okay, so let's see. I have one question saying, how do I know what can react with what? Which of these can react with NaOH but can't react with acid? So let's see, and I'm given those values. Okay, NaOH, which of these can react but can't react with acid? Okay. Let me just look at the different types that you're given. And you're given K2O. You're given calcium oxide. Okay. CO2 and carbon monoxide. Okay. So let's see what we can do. I would kind of look at them and just see what's the main difference between all of them. Yeah, hold on. Let me see what I can find with this. Let's see. So it can't react with acid. This is going to be H2SO4, and I would look at what probably won't be able to react. So I know that a salt would. So here, calcium oxide and aluminum oxide. And actually, better yet, I want to see what would have been soluble and what would have not been soluble. So let me open up my solubility table. Okay, I'll open up my solubility table and see what I can find with this. So carbon monoxide, that's a type of gas. And then K2O, that's actually a type of salt, but this would have been aqueous, I believe. Yeah. This would have been aqueous as well, but that's once again a type of salt. And then with aluminum, that's typically not going to be, this would have been a gas. Actually, I don't want to look at it that way. Kind of want to see what would form. Let me reread your question. But what's able to react, what's not able to react. I know the salts will be able to. Sorry, give me a second to just wrap my mind around this. And we're not reacting with acid. This is a weak acid. Okay. I know this is a weak acid. And I can see what else I can form with this. Give me a second to think about this one. Yeah, because I'm looking at different balance equations that I can do with this. Here. SO4. I know it's a weak acid, or actually it's a strong acid, This wouldn't be able to react with, I would say, a type of gas. Now, which of these, but can't react, got it. It can react with a strong base, but it can't react with an acid. So I know that some sort of salt would be able to. So I feel that those are out here. Just thinking about the process of it. So I know that these salts would be fine to react with some sort of base. Now, what I'm speculating is these gases. So whether or not the gases would be able to react with it, because even looking at it, how would you react those two together? Yeah, so I would have said that the ones that can react with that acid would have been our salts. However, an acid and some sort of gas doesn't seem to be able to react. So a lot of times what would react with an acid is either a salt or a base, rather than some sort of gas. So that's pretty much what you would look at. I just looked at the different states that they're possibly going to be in. I know carbon monoxide and carbon dioxide are types of gases, and however, an acid H2SO4, I knew this was an acid because it has that hydrogen in front. And that's actually pretty much it. So that's something to kind of look at. I would just say the gases overall. Okay, hope that makes some more sense. All right, guys. So I want to know from you guys, because we did get a good amount of questions here. So I would love to know from you guys if you, because I'm thinking about stopping the Sundays just for a little bit, just for the summer. And only coming a couple times on, doing the live. And then of course, next semester, I'm going to be doing that every single week. But I want to know when your guys' finals are. So let me know in the chat when your final or next exam or so on, just so I can see what to do about the live sessions. So yeah, please let me know in the chat right now when your final is, or, if you have an exam coming up, something about that, just because I don't know if I'm going to have next Sunday be another live Q&A, or if I'm going to kind of postpone that later. Okay, so this will pretty much depend on what your guys' answer is. But yeah, definitely let me know in the chat. I see the Evolving Vegan is saying June 12th is my final. Okay, yeah, please keep letting me know when your final is, just so I can see to be here. Okay. So yeah, but that is today's Q&A. I will keep you posted on next Sunday, June 22nd. Okay, got it. So just good to know. And then, yeah, I would keep you guys posted. And then I would also make sure to, if you haven't already, make sure to turn on your notifications, that little bell, because that tells you when I'm going live. So make sure to turn that on just to kind of give you a reminder when I will be going live. Okay, so make sure to let me know. And then, yeah, I'll see you guys hopefully next Sunday. If not, I will announce it in the community tab. All right, so I'll see you guys. Have a great day.